Hello, this short clip is designed to cover some of the aspects of how to name arenes or benzene related compounds, and also an introduction to the electrophilic substitution mechanism that you'll need to know for your A2 year. So we won't be looking at the Kekulé structure or the theory behind the Kekulé structure, or why indeed it's actually slightly incorrect, because this video as well assumes that you've had a look at that already. So we're simply interested in how to name some simple examples of arene compounds, and also how the electrophilic substitution mechanism works. So first of all, let's look at the basic benzene ring. It's going to look like this. And it can also be represented like this. And as you'll know by now, it can form two resonance structures. Let's change that, sorry. I was drawing the same thing twice there. Let's do it a bit better. So basically, as a quick review, what can happen in these resonance structures, if we assume that each of the three carbon-carbon double bonds in those rings, the electrons can move like that. And then the one on the left can form the one on the right. And then that can go back again. So it moves back and forth between those two possible structure, but doesn't stay on either one. So that's where the Kekulé idea wasn't quite right, because which of the two is it going to stay at? So like I said, I wasn't going to get drawn into going through why the Kekulé idea originally was actually wrong and ended up being proven to be incorrect. We want to make sure that we're happy with the benzene structure, simply drawn as a hexagon with a circle drawn inside it to represent the pi ring. So this is basically C6H6, and the circle inside the ring represents the pi system of electrons. So what would happen if you had a benzene ring where you added something like a methyl group to it, like this? This would now become methyl benzene. So no surprises there, of course. What would now happen if you had a benzene ring with an ethyl group, like this? No surprises for guessing that would be ethyl benzene. So if you were to now take a benzene ring and maybe put a chlorine onto it, that would obviously now be chlorobenzene. So let's now look at multiple substitutions. So we're going to take the examples we got on the left hand side of the screen and start to add more substitutions onto the ring. So bear in mind that each time you have a CH3 on a benzene ring, you've taken the hydrogen off it and put the CH3 on. If you have a chlorine on a benzene ring, you've taken the hydrogen off it and put the chlorine on. If you have an ethyl group on a benzene ring, you've taken the hydrogen off and put the ethyl on. So it's an important reminder there. So if we take our methyl benzene and we add a chlorine, let's say we add it here. What we've now got to do is think to ourselves, how do we decide where the chlorine is? Is this on carbon number 3? Or is it on carbon number 5? So in other words, do we name the ring clockwise, or do we name the ring anti-clockwise? So this now gives us two possibilities. If we name it clockwise, we then call it 3-chloro-methylbenzene. That's meant to read as a benzene, I'm sorry, it's gone off the screen. If we read it anti-clockwise, it would now become 5-chloro-methylbenzene. So in actual fact, this one is correct because it has the lower number, and this one is incorrect because it's got the higher number. So if we rub this off and put another example on there, we'll put a couple on there just to illustrate this a little bit more clearly for you. So just remember, we're always looking at the lowest possible number in the name as opposed to the higher two options. So there's no particular hard and fast rule about counting clockwise or anti-clockwise, provided you end up with the lower of the two numbers. So I'm just going to put down two just completely random arene compounds. And then I'll put the names for them. So the first one would be 3-bromo-chlorobenzene, and the second one would be 2-iodo-ethylbenzene. Because if we take the numbering like so, that's where the numbers come from. Sorry, I need to slightly change that. Practice what I preach, eh? So it should really be like that. 1, 2, 3, 4, 5, and 6. Okay, so now let's have a look at the reactions of arenes. So here we're looking at how an electrophile behaves. You've got to remember what an electrophile is from earlier on in the AS year. It's basically any species that can accept an electron pair, as opposed to a nucleophile, which is any species which can donate an electron pair. So what happens is we have our benzene ring, like that, and we have our electrophile nearby. So the first thing that happens is a pair of electrons come out of the pi system. So in some way, shape or form, the curly arrow must touch the pi system. So in other words, it can't just come from between the pi system and the outline of the hexagon. So let's say if you were to do it wrong, I'm going to slightly change it now to show what it might look like if you did it wrong. So if you were to do it like this, for example, that would be wrong. So we don't do that. We need to make sure that the curly arrow comes from either within or touching the ring. So another way of doing it, that's also okay, would be this, where it's just touching the outside of the ring. That's fine as well. So it's important as we go to make sure we're not dropping into making mistakes and picking up habits that could lose us marks. Because this is, like any other mechanism, a 4-mark answer. We need to make sure we're getting it right from the start. So what happens next? Well, we have our hexagon, just like before, but this time we draw a horseshoe shape. Now the horseshoe shape has to point towards the carbon next to where the electrophile was sitting. So the electrophile was in the top right hand corner. For want of a better way of describing it, in this case it's slightly northeast. Okay, so in other words, we draw the hydrogen and we draw the electrophile. We don't give it a positive charge because the positive charge has been distributed into the pi system. So we now have a partially delocalized pi system. So that pi system has to be restored somehow, and the way it happens is that the bond between the hydrogen and the carbon it was attached to breaks. That electron pair moves back into the partially delocalized pi system, and the pi system is now restored like so. The electrophile is attached, substitution in other words, and the hydrogen comes off as a proton. So in other words, if you were to draw it like this, and it was like that, that would be wrong. If you were to draw it like this, that would also be wrong. So what am I trying to get at here? Basically, you need to imagine a dotted line, or even just a straight line like that, and your horseshoe shape should line up with it like so. Okay? Now when I'm talking about the location of substitution, I mean the actual carbon atom where the substitution is taking place. So in other words, here. Okay? So, another video will cover what different types of electrophiles might actually be powerful enough to do this, because as we've already looked at, the benzene ring is quite stable, so in other words it's quite difficult to get it to undergo this type of mechanism. So suffice to say, just for the moment, it might be worth making note that only certain electrophiles are powerful enough to make this happen.